So in last lecture, we discussed about the theory of moving frames. So we discussed that if we have a frame which is denoted by this calligraphic F, and the subscript represents that it is the fixed frame, it can be represented by two or three if we discuss the three-dimensional space, three unit vectors E1 hat, E2 hat, and there was another frame of reference E1 dash hat and E2 dash hat and E3 dash hat. So then we took a vector in space which was this Q vector. Okay, so we had this Q vector. This Q vector has nothing to do with the frames, but we discussed that we can define this Q in different frames. We can describe it in this moving frame, and we can describe this in fixed frame. By which we mean that we can take the components of Q in fixed and the rotated in this moving frame. To be specific, we call this as the body fixed frame because this we usually fix with the rigid body. And then we discussed that how we can find the derivative of this Q with respect to the fixed frame, because generally what we will be doing is that we will be applying the Newton's first law, that is linear momentum balance equation and the angular momentum balance equation in the fixed frame or the inertial frame. But usually what will be available to us will be the information or the derivative of the vectors in the body fixed frame. So how we will be going to calculate this Q dot or the rate of change of this vector Q if it is given that what is its rate in with respect to the body frame. We need to find its derivative with respect to the fixed frame. So we found that could be done using this formula. So if we have some general Q vector, the derivative of the Q vector with respect to the fixed frame or the inertial frame, this can be any frame. So if we have two frames, let's suppose both of them are not non-inertial frames. So we can find the derivative of any general vector Q in one frame, that is F frame, as the derivative of the vector in another frame, that is B frame, plus the angular velocity of the this second frame, that is B frame, with respect to the first frame. And to be specific with this case, we have this fixed frame, so the derivative of Q with respect to fixed frame is equal to the derivative of this derivative of the vector in body frame plus the angular velocity of the body frame with respect to fixed frame cross product with the vector itself. And so then we discussed velocity of point if it is given in body frame, how we can calculate the velocity of a point in inertial frame. So this is also known as 3-point formula for calculating the velocity. We defined what is relative velocity. And similarly, using this, we calculated the acceleration for the point if we are given the acceleration of the point in body frame. So we saw that there were 5 terms. The first was the acceleration of the reference point, which is attached to the body frame and which is moving along with the body frame. And then there was the acceleration of the point with respect to the body frame, that is relative acceleration. And then there was this term coming up, and we call this term as the Coriolis acceleration, because there are other 2 terms like this one, and this was tangential acceleration, which we are known about. So, and this is the centripetal acceleration, but this term is something which we don't know, and this is known as the Coriolis acceleration. And we also saw that this effect can be seen if we move on a. So we are two friends, and one of my friend is staying diametrically opposite on a circular track which is moving, and so I am throwing a ball towards him. So due to the rotation, we can see if I throw the ball straight, a person which is outside this frame, he will see that the ball is uh, going straight on a straight line. But this B will have moved to this position. So the B will see as if the ball is going lateral, sideways, lateral in this lateral direction. So this effect can't be understood using the Newton's first law, the second law. So because if there is no force, a body should move in a straight line. So for A and B, if they are attached to a frame which is rotating, so they can't give any justification. But a person which is outside, he can clearly see that since there is no force on the ball, so the ball is moving in straight line. So this is what we call as the Coriolis acceleration. Okay, so this and then we did one more thing. We took a vector or not, and we were interested in finding a vector if this r naught is rotated by some angle theta about some axis in 3D, the direction of the axis is given by n hat. So if this r naught is rotated about this n hat by angle theta, so what will be the vector? So because we know if there is a vector in space, am I audible?
Yes, it is.
So if there is a vector in space, so if and by vector, I mean an arrow. So this is an arrow in space. And if I rotate it about some, say this is my n cap and I rotate it about, so this arrow will be shifted to a new direction. So now this arrow represents a new vector. And I will call that vector as r. So initially we have this r naught vector, and I rotated it about this n axis, and we got r vector, that is some another vector, rotated version of this r naught. And we did some mathematical manipulation, and we found that we can find out that new vector rotated version of r naught. So this was all the stuff which we did in last class. And we found out that this is the relation. So if we have r naught and we rotate it by theta about this n, so this formula will give us what is the new vector which we will get if we rotate it. Today, let us continue with the same, and we will see how we can use the dynamics and the Newton's law for the rotated like rigid bodies. Um, so, so I told you that this n is a vector, and I am placing these side by side. This means that it is a diode. And when we take the dot product of a diode with the or a tensor with a vector, we will get vector. So this whole is something which is a mathematical object. Like we have an arrow in space. No matter which frame you are using, this arrow will have its own identity. Although its representation will differ from one frame to the another frame, but it has its own identity. That is, it has a particular direction and it has some length that is not going to change. So we call this as a geometrical object. Similarly, we have something which is made up of these geometrical objects. See this n cap, this is a geometrical object. This is an arrow, this is an arrow. And here it was omega, if you correctly remember. Sorry, it was a cross product, which is also vector n. So all these things were something which were comprised of vectors, and this I, which is the unit vector, unit tensor, this also is a combination of vectors. So all these things are some combination of vectors. Maybe some one vector is like this, and I am putting another vector. But since vectors have their geometrical interpretation, anything which is made of vectors will have its geometrical interpretation. I am not concerned with showing what is the geometrical interpretation of this tensor, but just I want to make the point that this thing has a geometrical interpretation, and it is a geometrical thing which is not going to change if you change the frame. Although representation may change from one frame to another frame, but it will not lose its identity. It will have some magnitude, it will have some direction. Not just like a vector, like vector has some direction and it has a magnitude in a particular direction. That is not going to be the case. Or maybe in 3 dimensions, we have a vector which has 3 components along x, y, and z axis. But for this tensor, it will have, we will see how it is going to be different from a usual vector. So this is a tensor. So what we have? So what we have got is we have some R0 initial vector, and we rotate it, and we get the new vector, rotated vector R. And this is the rotation tensor, which give us this new rotated vector from the original vector. And this tensor is the function of the theta, and it is the function of this n about which you are going to rotate your vector. And it makes sense. This new rotated vector should be function of these things. That is how much you are going to rotate and about what you are going to rotate. So this R tensor is function of n, and it is function of theta. Okay. Yeah. Any question?
No, sir. I was just saying that it is a function of theta and n. Yes, sir.
Yeah. So basically, we have what we have got is that we have some R0, and we are feeding this to a function which is function of n and theta, and maybe it is also a function of R0. Maybe it is also a function of R0. So let's consider R0 also. Okay, and we should get R0. Or should I not include? Let me see. Okay. So here is n. No, so there is no R0. Yeah. So let's not take R0. R0 being only the input. So let's power up this. Okay, so we have got a function to which we give R naught as input and it is returning us R as the output. That is the rotated vector. Okay, so let us see closely in matrix or in like if we are going to code these things, how this R will look like. Okay. So in MATLAB, we can take this R can take this R as oh, I don't know what something is wrong with this. Let me try to fix it. So are you able to see what I am writing?
Sir, it is only or vector is equal to.
Oh, okay, I have not written anything, so you should not be able to see anything. Okay, so in MATLAB, like we can write the components for this R as what is happening with this? We can write this R as Rx. I think I have to close this whiteboard and log in again because it is making some trouble. Okay, just wait a minute. I will reconnect it. So let us see how this R looks like. Okay, so this is our formula to calculate this R, and we will see how it looks. Okay, so let me copy it. So, so our this is our R tensor. So let us see how we can write this R tensor. So we have this n, where n is a vector, unit vector about which we are going to rotate our this R naught. So it will have three components. So nx, ny, and nz. And we know if we have a diode like nn, it means a diode are the outer product in terms of the matrices. So dyadic product we know can be written as. So I am just focusing on the components only. So let me write that this is components only. So this is not a vector. There is a difference. So I can write it as n and n transpose, which is nothing but nx, ny, and nz. And this is nx, ny, and nz. So this is the outer product of this these n and n. So we can write it as, so this times this will be nx square. This times this will be nx ny. This time this will be nx nz. Similarly, this is nx ny. So on. I will not write whole thing because you can expand it in the similar fashion. So this is this n if you take in the matrix form or in the MATLAB, so you can write. And then there is this identity tensor. So in matrix form, this identity matrix is nothing but identity matrix. So this is our identity tensor. And then there is this n. So this n represents the skew-symmetric matrix associated with this n. So what is this skew-symmetric matrix? So if we have any vector n, so it will have three components, nx, ny, and nz. So skew-symmetric matrix associated with such vector is zeros on the diagonal, and then there is minus ny, nx, nz, and ny, and nx. Hope I am writing correct. Thanks, because sometimes you can make mistake. Yeah, it is correct. So this is the skew-symmetric matrix associated with this vector. So if you substitute these all things here, and obviously the theta is a scalar thing. So instead of this tensor, you will get a 3x3 if we are dealing rotation in 3D. So you will get a 3x3 matrix instead of this thing. From here, you will get 3x3. You can see it here.
Sir, S and skew symmetric matrix of n.
Yeah.
Sir, how you derive this skew symmetry matrix of n?
Yeah,
Uh,
this is this is a nice question. I think in one or two classes back, I gave it as a homework problem that you calculate this. But yeah, I will give an intuitive way. I will not solve this whole, but yeah, I will provide some intuition where you can go and solve this thing. Like how this skew symmetric is this thing. Yeah, I will go and give you a starting point from where you can get it. Okay. But yeah, it
okay,
is
sir.
intensively used when you are dealing with the vectors and tensors. Okay, so I was saying that if you take n and n uh, in the component Y, so you will get a 3x3 matrix. And here also you have a 3x3 matrix. And here also you have a 3x3 matrix. So you add three cross matrices, you will get a 3x3 matrix. So this rotation tensor in component in a particular frame will be a 3x3 matrix. Okay, and your R naught will be a 3x1 vector. Okay. So now let's see few examples which will illustrate like what we are saying, how it matches with the 2D things which we have already done. So let's take a 2D case. So let us say we have x-axis and we have y-axis. So this x-axis can be represented by E1 hat, and this can be represented by E2 hat. And we have some rigid body. Okay, we have some rigid body. Okay, let's say this is R naught, and this rigid body is rotating only about this plane. That is, it is rotating in XY plane. So its axis will be in Z direction. So omega will have its direction in Z direction, so it will be K. But here in the generalized way, the axis of rotation was called as n cap. So n cap is equal to K hat. So what will be this R naught? What will be the rotator? So if we rotate it by some theta, it will go to this position. So what will be the new R? So the new R or the rotated R naught will be equal to R dot times R naught. What is this R naught? R, this is equal to 1 minus
One
cos of theta
n n n into
n cap, yeah, plus cos of theta
I
I plus
plus cos of sine theta
sin
sine
theta.
I.
Okay, so
Yes,
this is
sir.
our R. So let's calculate and see what this comes out. So we have seen that here for 2D case, the n is what is n? N is K. So what is this n cap? N cap, this n cap in matrix. In matrix, we can write it as, so it is k cap, which is nothing but k cap, its components, k cap transpose. That is the outer product of these two vectors. So we can write it as 0, 0, 1, and we can write it as 0, 0, 1. If we open this up, we can see that this is equal to 0, 0,
0,
all
0, 1.
zeros, all zeros, and here it is 1. Okay. So similarly, I, we know I is nothing but identity matrix. And let's see what this n schistometric matrix associated with this n is. So this is n, sorry, 0, 0, 0, and this is minus nx, minus nz, minus ny, nx, ny. Okay. So it is equal to 0, 0, 0, and minus nx. So what is the x component of n? N is k, and x component. So n is equal to k here, and the
Yes, sir.
component are 0, 0, 1. So the x component of n is 0. So it is 0. What is the y sorry, what is the y component? It is also 0. And the z is minus 1. So here
Minus
also
one.
it is 0, it is 1, and it is 0. So this is the schistometric matrix associated with the k or the n. Okay. So we got this, we got this, we got this. So let's solve and find out what this k is. Yeah. Is it clear what I am doing?
Yes, yes.
Yes, I think it should be clear. Okay, so the components of R, so I should write it like this. So the components of R are equal to 1 minus cos of theta. What is this n in components? It is 0, 0, 0, 0, 0. This thing 0, 0, 0, 0, zeros, all over zeros, and this is 1 plus cos of theta, and this is 1, 0, 0, 0, 1, 0, 0, 0, 1 plus sine theta, and n schistometry matrix is equal to 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay, and this will be equal to, so what is this? So everything is 0, only everything is 0. Only this term will be 1 minus cos of theta plus. So here also everything will be 0, only this will be cos of theta, and this will be cos of theta, and this will be cos of theta plus. This will be 0, this will be sine of theta, this will be 0 minus sine of theta, this will be 0, 0, 0, and zeros. I hope I have not made any mistake, and
No, sir.
everything is. So this will be equal to. So all of these are 3 by 3 matrices. So I can add them component wise. So I can add this, this, and this. I will get cos of theta. This
Minus
is
sine of
cos of, and then there is minus sine of theta, and
0.
then there is 0. Then again there is 0. No,
Sorry,
sine of
sine
theta,
theta.
sine of theta, and here will be cos of theta, and here it will be
Then
0,
0.
and then there will be 0, 0, and 1 minus cos of theta plus cos of theta will cancel, and there will be 1 only. So nice. So we have got something which we are already familiar with, and I think we have calculated in one when we were dealing with the
Yes, sir.
2D motion. So this is FM's rotation matrices associated with
Exactly.
the rotation along the z-axis. So if you are
Exactly.
rotating something in 2D plane about z-axis by theta, so this is the rotation
Yes, yes.
matrix. Okay. So so in some of you may be thinking like we went to a very generalized thing, and then now we are again coming to some particular cases. So this is only that since this thing was very new, this rotation tensor. So to give a flavor that this is not a different thing, it is just similar to what we have already done. That is why I like I did this exercise for you. So similarly, you can check the rotation about the y-axis and the rotation about the z-axis, and you will get the rotation matrices along x, y, and z-axis also. So nice. So let's continue and see what about the derivatives. Okay. What about the velocities? So by the way, I think I have missed that this formula is no. This is a very famous formula, which so this one is very famous formula. I think I have not told it yet. So this is a very famous formula, and it is known as Rodrigues formula. So this is known as Rodrigues formula. Okay, so this is known as Rodrigues formula, who first calculated it. Okay, so now let's define. So this was a. So are you able to see this cubical box?
Sir, no, where is cubicle box?
Or you are not able to see?
Wait. Yes, sir.
So this
Yeah,
is a
yeah.
cubical box. Yeah.
Yes.
Okay. So this cubicle box, there was a vector associated. Okay. And we could move it in any direction, but at a particular instant of time, it will be rotating about a fixed axis. So you can rotate this, or I have another thing here. So let's take this bottle. So you can constantly rotate it about this axis, which is going like this. You can constantly
Yes.
rotate it about, but in general, it may rotate about this, and sometimes it may rotate about this and this. So at each instant of time, this will be rotating about some general axis, which may which may be known to you, or which not may be known to you. So what I mean is that if we have a body like this, and initially we know some vector are not associated with some point which is attached to this body, and now it has rotated about a fixed axis. So you can use the rotation matrix, rotation tensor associated with that given rotation theta and this axis, and you can find out where that point is now. That is, you can calculate a rotated vector for or not. But if there is a general rotation, so that n axis will not be a constant axis, and also, okay, n is not a constant axis, then you may not be able to find out um, you will not be able to find out some r which will take you from this initial to the final configuration. Although we have a formula that given we have some initial vector, we have some n about which we are going to rotate a body, and we have theta, so we can rotate a given object from initial to the final position. But so what we will be doing is that at any instant of time, the body will be rotating about a given axis. At a particular instant of time, it cannot rotate about some arbitrary, it will be rotating about any vector, but that will be fixed at that instant of time. So I am saying that the rotation at a particular instant of time is like it is rotating about some 2D plane. I don't know whether it makes sense to you, but it is like that. At a particular instant of time, the axis of the rotation will be fixed. So if the axis of the rotation is fixed, so what I will do, so let's assume, are you able to see?
Yeah, yes, sir.
Okay, so this was my R naught. And I am saying at any instant of time, let us say this body is rotating about this vector n. Okay, and for small period of time, this will be rotating about this n. This will not change for that small period of time, a small duration of time, I should say. So this R naught will shift it to this, and there will be some change in R. And this rotation will be small rotation delta theta. Okay.
Okay. Okay.
So this will be very small rotation. So what this delta R will be equal to? So this delta R will be
R
equal to,
R del theta. R del theta. Not R, sir. It radius.
okay, so can I say it will be equal to delta theta? Yeah, I know you are saying right, but can I write it like this?
N
Or
cross. Yes, sir. N cross
if I am
R
taking
naught.
this as R, so I can write it as delta theta n times R. Because not now it is not the initial R naught I am talking. I am talking about any general R at some intermediate time. So it will be some R, and it is at that instant of time, it is rotating delta theta about some axis n. And at that instant of time, I can say that the change in the R vector is delta theta R n cross R. So basically, what is this n cross?
Yes, sir. N cross R.
Yeah.
How
So this
how
change, yeah. So basically the change is taking place in the plane of this rotation plane. So if I draw this, so the change will occur in this plane. But the change I know will be equal to this radius of the circle times the theta. So basically radius times the theta. But I know that if I take the cross product of n with r, it will give me this radius, which we have, I think in previous class we have discussed that the magnitude of this thing is the radius of this circle. Okay. Again,
okay.
so basically this change is nothing but r, which is correct, and we multiply it by delta theta. So this delta r magnitude will be r theta, r delta theta, but the direction will be in the same direction as n cross r, which is tangential to this circle. So this will be the delta r, and if we divide it by delta t and take delta t, limit of delta t tending to 0, so this will be r dot, and this will be theta dot n cross r. Okay, so this is theta dot. So this is the definition of omega. This is the definition of omega. So what is the definition of omega? It is the rate of change of the angle,
Radial.
but don't be deceived that there is some function theta. There is some function theta of t, which you are differentiating, and you are getting this omega. No, that is not correct. That is a wrong perception. So at a given instant of time, you can take theta to be something as a vector, and you are calculating its change. and you
That
are
is
taking
omega.
the derivative. So that is your omega. There is no such history of theta which you will differentiate and you will get this omega. Okay.
Yes,
So
yes. I got.
so this function I already have, this equation I already have explained in 2D that this is a very general function. So the rate of change of position is equal to the omega of the body cross the position itself. Okay. So yeah. Okay, so let's proceed and see what we have further things. So yeah, now I can write this. I can write this thing as omega tensor or the skew symmetric omega associated with this omega vector dot r. Okay, where this is skew symmetric matrix or the tensor you can say with associated with this omega. Why I'm saying it is a tensor is because it will have different components in different frames, but it is something which is not depending upon the frame itself. Okay. So which will determine this omega? It will be determined by the n, and n is in itself is not dependent on the frame. Okay, so skew symmetric matrix associated with omega. So omega will have some components. Omega x, omega y, and omega z. So take these components and write its symmetric matrix as I did for n. So substitute it here, so you will get this.
Skew symmetric of omega.
What?
Why we are taking the skew symmetric of the omega?
Basically, here it is the cross product. Okay. So what I want to do, I want to so if I am dealing with the matrices, I need some matrix. I need two matrices which I can multiply with. So associated with this omega, I have this symmetric matrix, which I can take dot product with the column vector. Okay. Are you getting my point? Otherwise, you have to take cross product, and MATLAB does not know how to take a cross product. Although there are functions you may say, I can write a cross of omega cross r. Yeah, you can write, but inside it, it is doing similar thing. That is, it is creating a symmetric matrix, and it is just making a dot product of the two, are the matrix multiplication of the two matrices. Okay, is it
Okay.
clear?
Yes.
Okay. So let's do one thing. So if I have a frame, say this is E1, this is E2, and this is E3. Okay. And there is another frame. I have got this another frame by rotating this frame. Say this is fixed and this is rotated frame. I call this as E1 dash, E2 dash, and E3 dash. So basically, if this is E1, I have rotated this E1 to get E1 dash. I have rotated this E2 to get E2 dash. Similarly, this. So there should be a rotation tensor associated with this. So I claim that that rotation tensor is equal to E1 dash dot E1 . Just a second.
Sorry, can you make ink little bit more darker?
So I think it is dark, but I think its size is it is 100%. So what else can I do? This is the maximum. I think there is some problem with, I don't know with this. Okay, I will disconnect it, but let me see if I can disconnect it. Reconnect it. I think it is not visible, or it is visible but not comfortable.
It is visible. It is visible. Yeah, yeah, not compatible.
Okay.
Okay, sir.
So okay,
Can customize it.
okay. Okay. So this R is a tensor. So to give it a feel that it is something which has nothing to do with the components. So this R is equal to E1 dash E1 plus E2 dash E2 plus E3 dash E3. Okay. So now if you have a vector, any vector you take, you have vector Q. Okay. So if it is attached to this frame and you rotate this frame, so this Q will also get rotated with respect to this fixed frame. And you want what is the components of Q in this fixed frame. Or first, you may be interested what is the vector Q in itself? What is the rotated vector? So forget about the components. So the rotated vector will be equal to R dot cube. What is this R? It is a tensor. What is this tensor? And this tensor is this. So I had put the vector side by side. If I take the dot product with Q, so basically what it will be? So it will be equal to E1 dash E1 plus E2 dash E2 plus E3 dash E3 dot Q. And by definition, it is E1 dot Q. By definition of diodes, E2 dot Q plus E3 dash E3 dot Q. Okay, so this is what this rotated thing or the rotation tensor did to this Q vector. Okay, so if you can think about it a little bit, you will see that this Q vector taking the dot product with E1 gives its component along the E1. Similarly, its component along the E2. Similarly, its component along the E3. And you have E1 dash, E2 dash, and E3 dash. This is how this vector will look like. But if you want its component in any particular frame, then you have to change this E1 dash, E2 dash, and E3 dash. For example, if you want its component just in this frame, then this is it. But if you want its component in this frame, then you have to change E1 dash, E2 dash, and E3 dash to this frame. That is in terms of E1, E2, and E3. Okay, you can check one thing I will because I have a limited time. So, but you can check that this rotation tensor in components, you can write it as E1, and it is very powerful to write it like this: E1 dash, E2, E1 dash, E3, E2 dash, E2 dash, and E2 dash dot E1 dot E2 dot E3. So E3 dash dot E1. Okay, so this is the rotation rotation matrix represented in terms of the components. So what is this? This is the components of new frame along x-axis, along y-axis, and along z-axis. Along x-axis, along y-axis. The components of the new x-axis about x, y, and z. The components of the new y-axis along x, y, and z. The components of the z-axis about x, y, and z. So if you do this, you will see that it also corresponds to the same rotation matrix which we have already derived. Like if you take the about z-axis, so take rotation about z-axis. Say the rotation is about zx, so E3 dash will be equal to E3 itself because you are not changing it. But you have x, so you have E1, you have E2, and you have E3. So you are rotating about E3. So your E3 dash will also be in this direction, but you are rotating. So your E1 will be somewhere here, and your E2 will be somewhere here, and this will be theta. So in terms of, you can write E1 in terms of E1 and E2 as cos of theta and, sorry, so you can write E1 dash as cos of theta E1 plus sine of theta E2. Similarly, you can write E2 dash as, you can write E2 dash as minus cos of theta E1 plus sine of theta E2. Okay. Oh, I think I make mistake here. It should be sine of theta.
Yes,
And
yes,
it should be cos of theta because this will be theta.
yes,
Okay.
now
So you have E3 equal to E3 dash, you have E1 dash. So you can calculate these dot products. So you can take E1 dot E1 dash dot E1. So basically you have to take E1 dash dot this vector with E1, you will get this thing. Okay, let me evaluate first term and then rest of things you will do. So E1 dash dot E1 is equal to, so this is E1. So this will be cos of theta E1 plus sine of theta E2 dot it with E1. So this will be equal to E1 dot E1 is 1, that is cos of theta. E2 dot E, that is 0. So we will, so this term is nothing but cos of theta. Okay. Similarly, you can evaluate other things. When you evaluate the whole matrix, you will see that this will be cos theta, this will be minus sine theta, this will be sine theta, and this will be cos theta, this will 0, this will be 0, this will be 0, this will be 0, and this will be 1. And that is the previous matrix which we have already got. Okay. So since we are running out of time, we have, I think, only half an hour left. So let me quickly shift towards the dynamics part, how we are going to solve the dynamics with the rigid body. Okay. So we have for a rigid body, let's take this is the center of mass. So we know linear momentum balance equation says that F total external.
what we are doing now, sir?
Yeah.
What we are doing?
What we have to, I'm not. What we will be discussing, yeah?
Yes, yes, sir, yes, sir.
Okay, that is what I am trying to say. I am not finished it.
Okay, okay.
So till now, what we were doing, we were taking point objects and we were applying some force on that, and the body was moving, and we were calculating what is the new position of the body. This is the whole essence of this course. But and then we did some rigid body motion, but that was restricted to 2D only. So we had a body, and that was rotating only like this, and it was moving and it was rotating. Okay, but this was only restricted to 2D. So now we are shifting towards 3D. We have a very general body, say this or say this. We have a general body. It is doing like this and it is going around. So basically, what is happening? You are applying some force. This body has some center of mass, which I am saying it is G, and you are applying force. Under the application of this force, and there might be other forces also, this body will move. And how it is going to move, that we want to see. Okay. So we know that if there are some F1, F2, Fn forces. So F total external. What is the net external force? That will be M total. That is what is the total mass of this body times acceleration of G. And this gives us the dynamics for the center of mass. So this equation in itself is enough, given the initial conditions also. If we are given the initial condition, what is the initial velocity of the center of mass? What is the position of the center of mass? So this equation is sufficient to predict what will be the future trajectory of the center of mass. Okay. But what about the motion about the center of mass? Okay, we are applying some external forces. This equation is telling us how the position vector is changing. This is good, but it is only saying how the position vector of center mass is changing. It is not telling about how this cap is going to move along the way. Okay, but we have I think when we started the 3D rotation, I told you that the rigid body motion can be decomposed. We can decompose this rigid body motion in motion of center of mass or the translatory motion, okay, plus rotation about center of mass, okay. So we can treat as the dynamics at the position of every point, or the dynamics of the rigid body is completely determined if we have the motion of center of mass and we have the rotation of body about the center of mass. This is the enough information. So first this will give us the translatory part. Whatever I have written here, this equation will serve that purpose. So now the question is about second part, that is the rotation about the center of mass. So we know the net external moment about some point C is equal to the angular momentum of body about that point. So if we have any general point C, if we have any general point about C on this body, the net torque due to these external forces about this reference point C is equal to the angular momentum of this body about the point C. But it is not a trivial thing. Why? Because this angular momentum about C is something in which we can make a mistake. But we have seen that if we have a very good reference point, say for example, C point is in itself a center of gravity point, or C point is some fixed point, or C point is a point which is moving which is the acceleration parallel to the center of gravity, then these are some good points which we can take as the reference. But let's take center of mass as the C. So we can write M is equal to H with respect to G. Okay. Okay, but going beyond this, let me first again make you understand why we are doing this. What was your question also? So basically, we had initially a particle, and we know its position r naught. That is the initial position of this particle. And we know what is its initial velocity. Say, for example, it is moving in this direction. We want its position at any time t. What is its position? Okay. So how we did? We did it in the reverse way. We saw that if there are some forces, say some forces F, we use the constitutive law to calculate the acceleration. The acceleration was equal to F upon m. And this is nothing but r double dot. Then we integrated this r double dot to get r dot, which is nothing but the velocity of this point. And then we integrated this velocity to get our position at any time t. This is what, and then we use that information to simulate the things. This is what was the general agenda for the course. But now what we in this part, what we are trying to do, okay, this is for center of mass, but we want to do it for other points also. So there is a general point here, and I know that this body is moving and it is also rotating. And I know what is the future position of the center of mass, but I don't know what is the future position of this point P. Okay, so I want to find out this. And you may say that, okay, if initially I know its position is R naught with respect to center of mass, and I have omega, so I know that R at some other instant of point when this body will move, that R will be equal to rotated R will be equal to rotation tensor times R naught or not. You may say like this, and this R will be equal to function of theta and n, which should be known to you. Okay, it is fine if it is known to you. And then I may say that this n is continuously changing. So you can say that we have R dot, which is equal to R dot times R naught. Sorry, R. It is at any instant of time. So you can say that I will integrate this to get this. But the point is that how you are going to calculate this R dot. You don't know how this is like how it is varying. Similar to the fashion which is here, you don't know velocity. So what you know is, you know constitutive laws. You know what is the external force and what is the acceleration. This is basically the essence of second law. So second law connects the things on the upper level. That is, it connects the acceleration. You have to integrate the acceleration to get the single derivative, and then you have to integrate it to get the velocity. So to get the position. In the similar fashion, you will be calculating something, and like omega dot you will be calculating. You will integrate that, you will get this R and R dot, because R dot is nothing. Okay, I will show you that this R dot is, or I think I have shown it. If I have not shown it, I will show it. This R dot is omega cross R. So we will try to find out this omega. But this omega in itself will not be known, so we will try to calculate omega dot. And how? So the agenda is to find the omega dot. Once we get the omega dot, we will integrate to find out omega. And once we find the omega, we will find out R dot. Once we find out R dot, we will find R. This is small r dot, and this is capital R dot. So when we find the capital R dot, we will integrate it to get our R. So this is the bigger picture of this portion of talk. Okay. So how we are going to do this? So that is what I am trying to make you understand. Okay, so the external talk about the center of mass is this thing. And we know that H, this is dot. So H with respect to G is equal to, we have seen this position with respect to G of each point. So if you take any point, say P, and you take its position with respect to G, so there will be small mass dm. So you take R with respect to G, cross it with a relative velocity of P point with respect to G, and take so this is basically velocity of small mass dm, R cross velocity of small mass dm, and you integrate this for the whole body. You integrate it for the whole body, okay? And this will give you the angular momentum about the center of mass. And so what will be this equal to? So this will be equal to R with respect to center of mass cross. What is this R with respect to G dot? So the body is rotating about the center of mass with some omega, which we don't know, but it is moving with omega. And this R with respect to G. Okay, so this vector R with respect to G, this vector, it is also rotating, so it will change. So what is that change equal to? So we have calculated it. So R dot is nothing but R dot times R. So R with respect to G dot will be equal to R with respect to G, sorry, omega cross R with respect to G. Okay, put it here. So omega cross R with respect to G. Okay. So what will be the next thing? Next thing is so obvious that you should now predict it. So there is a cross product of three
Yes, sir.
vectors. So we will
Omega.
use, if we have A cross B cross C, three vectors. So
Back.
its cross product is back cab, back cab. Okay, where back is this and cab is this, and here it is dot, and here it is dot. Okay. Okay. So similarly, we will use it here. So this is equal to back. So back will be omega, and A is R with respect to G. I will drop this R with respect to G. This should be understood that it is with respect to G. In next step, I will not write it with respect to G. Okay, dot R with respect to G minus C, that is R with respect to G. What is A? It is R with respect to G dot R with respect to G dot what is B? It is omega. Okay. So this will be equal to omega R with respect to G dot R. A dot A is nothing but mod of A square. So this is mod of R square. I am dropping this G because it is understood. So similarly, this is R dot omega. Okay. So and DM I am missing somewhere. Yeah. Yeah. So it DM and it is DM. DM. So I can do one thing. I can write it in this form. I can write mod of r is nothing but it is magnitude. So I will write it r square times omega. But I will take omega as common and kept it outside the braces. So this is r vector. And I will write this r vectors side by side. And I will take this omega out. And I will make this identity. And I will take the dot with this vector. So you may say why you are doing this. It is only because I want to create some tensor. And I also know that omega of a body is not different for different points on the body. It is omega is associated with a rigid body and it is same for every point. So this omega I can pull out of this integration. That is the only thing I am doing. Okay, but while I am taking away, so I use make up the diode product. So this is r dot omega. So I can take this omega out and I can take this side by side. So this is r dot omega. If you come back by the definition of diodes, it is this thing. Similarly, here it was r square, which is just a scalar number. So it was omega actually here. I took omega away. So what left was identity matrix, identity tensor. Okay. So I should multiply omega with identity tensor. By identity tensor, I mean if you take the dot product of some vector with identity tensor, it will not change the vector. That is the definition of identity. Okay, tensor. So take this omega out of this integral. So I will get integral of this thing minus r dot r dm, and omega is just outside it. Okay, because this omega is constant. Omega is constant for all. This integration is over body. Remember this thing. And this omega is constant over the body, constant over body or constant for body. Okay. So I define, not I, this is defined as inertia tensor dot omega. And this is something which will not change. Like it will be changing if you take in a different frame, but for a given for a body frame, it will be a fixed thing, and it has a geometric meaning. That is a body which is a geometric thing. When it rotates, something that is its shape doesn't change. Similarly, this tensor has its own nature, has its own geometrical properties, which is not going to change over the frames. But its component will be different in different frames. Okay, and this is known as the inertia tensor. Any question till now?
Sir, no, sir.
No? No question?
Sir, in previous, when we define a rotation tensor,
Yeah.
sequence of that R is whenever you want to change a position of a point P, you just make a dot with R naught. You get a new position. You get a new rotation about theta. That was the significance of R naught. What is the significance of this I? If we dot any vector with this I, what will we get?
Okay, so what we are calculating, let us see what we are calculating. Actually, we were calculating angular momentum. Okay, so see what we have calculated and what is It is significant.
Movement
So
of
H with respect to G. Okay. And what was our equation? Our equation was external torque about G is H dot, where this H is
angular
I dot omega.
omega. It is m into v as in linear.
Okay, so this is dot. So this has a very good, this reveals a very good thing if you think over. That is maybe in your high schools or maybe in your 12th standard, you have mostly taken the one-to-one correspondence. So what is one-to-one correspondence? So let's see, because it is important. So I want to make this point here. So let's take linear thing and let's take angular thing. Okay.
Yes, yes.
Here we have a force. Here we have torque. Here we have mass. Here we have inertia.
Yes.
Here we have acceleration. Here we have angular acceleration. Here we have linear velocity. Here we have angular velocity.
Yes, sir.
Okay.
Yes, sir. We have position.
This is
R.
tensor. This is tensor. And here we have R, and here we have theta, which is not a vector. So this is not a vector. Okay. So
Yes,
yeah. And what else? Okay, yeah. So we have here we have an equation which is like this, and we directly write
I alpha.
in our high school we
I
write torque
alpha.
M as I times alpha.
Okay.
Okay. And this is so wrong
Eh?
that it takes your full age to erase this concept that it is wrong. Okay. This is not right thing to write. Okay. And one thing what we do is that okay, let me think. I just missed one thing. So another thing what we do is that we have momentum P, linear momentum equal to mass times velocity. And we write angular momentum as H as I times omega. Okay. Then we know that F is nothing but dP upon dt. And here we write tau is equal to dH upon dt. And since mass is constant, so this is dV upon dt.
Okay.
And here we write tau equal to we take I as constant and we write as d omega upon dt. And we get I alpha. Okay. And here we get M into A. This is what usually people do in high schools. Okay. And this is wrong. Let me say that this is wrong. This is not a good. Yeah.
Why?
Okay, let me see one thing. So why it is wrong? Let us see. So what does this mean? I is something which is which we usually. So basically, we are dealing with the 2D things in our high schools. Okay, so everything seems correct here. But once we jump into the 3D, so then these things does not remain valid. And the thing is that I is a tensor, and you take the dot product of I with omega. So I being a tensor, it is just like a rotation. Rotation is also a tensor. You will have a 3 by 3 components for that rotation. Similarly, this I will have some 3 by 3 components, and you are taking the dot product of omega. So this H angular momentum will not be in a direction as the direction of omega. So if this is a body, And let us say this is rotating about this vertical axis. Okay. So we know the angular velocity is along this axis. So you will close your eyes and say that angular momentum is also in this direction. Okay, it is fine. I also agree that for this case, the angular momentum is in this direction, angular velocity is in this direction. Okay, but this is not the general case. Your body, for example, is rotating like this. Okay, it is rotating like this. So angular vector is somewhere here. And you are rotating it with respect to the fixed frame. Someone may tell you what is the direction of the angular vector, angular momentum vector. Angular momentum vector will not point in the omega direction. Why? The reason is this. The reason is this. The angular momentum vector is not in the direction of omega. It is some rotated version of omega. And what causes the rotation? That is this inertia tensor. Depending upon what is the matrix for the inertia, the omega will be shifted. Okay. So this is very important point which you should keep in your mind. Okay,
Can I
so
say that?
yeah.
Can I say that? Likewise, we just to say that momentum when we have a direction of momentum is same as velocity, direction of velocity. But in this case, the direction of omega is not the direction of angular momentum is not same as direction of omega. It depends on the inertia.
Yeah, it depends upon the inertia. Yeah. So if you have an inertia tensor, say we have an inertia tensor which is 100,010,001. In some frame, we have inertia like this. Okay, I am again emphasizing that omega, this inertia tensor for a same body will have different values in different frames. So for example, take a fixed frame and say our body has, take this cube, and let's assume that its inertia about this axis is 1, about this axis is 1, and about this axis is 1. So when you rotate this cube, which is a very good cube having a symmetry that its inertia is same in every like in the three principal axes. So you will see for this cube the inertia matrix, this inertia matrix will have values like this. Okay, so it will have values 1, 0, 0, 0, 1, 0, 0, 0, 1. These are the principal values of inertia. Okay, and you are dotting it with omega, components of omega. And what you will get, and for suppose you have omega x, omega y, and omega z, which are the components along x, y, and z axis. So when you will dot it with this, you will find it is omega x, omega y, and omega z. So I have, not me, I mean inertia tensor I. So this I tensor have not rotated the omega. So your angular momentum vector for this good cube will be in the same direction as the omega itself. So if you rotate it, the direction of the angular momentum vector will point in the same direction as omega. And this will have consequences. For example, if you want to rotate it faster in some direction, you have to apply the torque in that direction. And since your angular momentum vector is same in the same direction, so you may take omega dot as same as like you have the torque vector. Okay, so this is what I try to make you understand. Okay, have you got it?
Okay.
Okay, so so this I tensor, you know, the identity tensor, this have values 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. And similarly, this R and R in matrix or in MATLAB, this R and R, for example, let R be some X, Y, and Z. So R and R, this is outer product, so this will be X, Y, and Z. X, Y, and Z. Okay, so you can evaluate this. What you will get? You will get X times X is X square, XY, and XZ. Similarly, you will get here. So you will get 9 components. Okay, so you have to so you will get basically what I'm trying to say. For inertia, you will get a 3x3 matrix. Okay, you will get a 3x3 matrix. And then using this equation, so what? So let's further do it and see what we will get. So basically, we have reached till this point. Yeah. So let us go beyond and see what we can get out of it. So we have M with respect to G is equal to H dot. Okay, but this is with respect to fixed. See, this H with respect to G is a vector. We can take it as derivative in any frame we want. We can take this derivative in body frame. We can take it as derivative in fixed frame. But when we are using this equation, we have to take it as derivative in fixed frame. Okay, in inertial frame, I mean to say. So we have already done in previous class that if we have some vector Q, its derivative in fixed frame is equal to its frame in body frame plus the angular velocity of body frame with respect to the fixed frame cross the vector itself. So we will use same. So we can write the derivative of H with respect to G in fixed frame is equal to H with respect to G in body frame plus omega for the body with respect to fixed cross this vector. Okay, so what is this vector? So what is this? So omega B with respect to F cross. What is this H with respect to G? So we just calculated that it is I dot omega. Okay, so okay, this is fine. But what about this? So let us see what this is. So H, this is basically, this is dot, yeah, I forget. We are calculating the rate, so it is dot. Okay, okay. So what is this? So H dot with respect to G. So this is equal to omega in body frame d by dt of, what is H with respect to G? It is I dot omega. Is it?
Fixed frame.
Okay, so this can be written as d by dt of this thing, this. So d by dt of I dot omega plus d by dt this times d by dt of omega. Okay, and this is equal to. So I already told you that in body frame, see, this is a body and it will have some inertia tensor associated with this body. There will be some inertia associated, and that inertia tensor will not be changing with respect to this body. If this body is changing, this is changing, but it is not changing with respect to the body frame. So there will be no inertia tensor change with respect to the body frame. So this will be equal to 0. So this term vanishes. So we are left over with this only. I dot, what is this? This is omega dot. Okay. And this is in body frame. Just a second. And this is, we are taking with respect to the body frame. So this is with respect to the body frame. And this omega is omega of what? It is our body. So we are taking the derivative of body frame with respect to the inertial frame. See, try to understand what I am saying. The omega vector, and omega vector has been defined as the rotation of the body frame with respect to the inertial frame. But I am taking the change of that vector. That vector will point in some direction. I am taking that change with respect to the body frame. I am saying how that vector, that omega vector is changing with respect to the body frame. First, I define the omega with respect to the inertial frame, but now I am taking the derivative with respect to the body frame. Okay, so
0.
Okay, say.
It is 0?
No, it is not 0. Let us see what this is equal to. So we have Q in fixed frame is equal to Q in body frame plus omega body cross the vector. So I can write omega body with in fixed frame is equal to omega with respect to fixed frame, sorry, with respect to body frame of cross omega. Okay, so what is this equal to? Omega cross omega. This is 0. So what is this? This is a very nice, which your mind will not accept, but it is. So the rate of change of angular momentum vector with respect to the fixed frame is equal to the rate of change of omega vector with respect to the body frame. This is the only vector whose rate is equal in both frames. So if you take the angular momentum vector and you are seeing it change with respect to the body frame, or you are seeing it change with respect to a fixed frame, both are same. Okay, so I can replace this and I can write it as I dot omega. See, this is, subscript B represents omega body with respect to fixed frame. Okay, so I should write it body with respect to fixed body with respect, and this upper B represents that frame in which you are taking the derivative. Okay, so now we have got this equation. So what is our equation? The external torque is equal to I think this is becoming little bit. I think it is not visible now. Yeah.
No, it is visible, sir.
It is visible,
but not so much.
Okay, but this is very important equation, so I don't want to like miss anything. So, okay, let us see. Let me zoom it out. Zoom in. Let's see what happens. Okay, so this external torque is B H dot with respect to G. So, but this we have evaluated and we have got this. So this is equal to but this is also equal to the fixed. So I can write here fixed dot with respect to body with respect to fixed plus omega body with respect to fixed cross inertia tensor of body dot omega. So this is a very important equation. Okay, why? I will say why. The first important equation is F equal to ma. The next important equation is this. Together, if you take these equations together, you can solve any general rigid body dynamics problem. So these are very important. So what is this? This is external torque about some point about center of mass G is equal to inertia tensor dot rate of change of angular velocity of body with respect to fixed frame taken in fixed frame plus the angular velocity of the body with respect to fixed frame cross the inertia tensor dot omega. So from this equation, what you will get omega dot, a body. Okay, so you will get this. How? You will get this like this mg minus omega b cross I dot omega. I inverse. So I take this on this side and subtracted it. Then I take this and take its inverse. Okay. I took its inverse. So I got omega dot. So I can get this m with respect to g. I know the external forces. I know how to calculate the torque about some point. So I can get this m with respect to g. And I can solve this equation. And I know the initial condition. So I can solve this equation to get omega dot. Once I get the omega dot, I can integrate it to get omega. So I know omega dot. I can integrate it to get omega. So integrate this omega dot to get omega. Okay. And if you
Yes, sir.
got, if you got the omega, so what next you can do? You have r
And
dot, which is equal to omega dot omega dot r. So r omega cross r. So omega cross r. So you can integrate this omega r dot to get r. And when you have r, then you can use this equation. R is equal to r dot r or not. Okay. So in this way, now you have got the dynamics of the center of mass and you have got the dynamics of every point. So you can plot every point. So this was the framework in which you have to work. Okay. So you can do a lot of things if you simulate these things. You simulate. You can simulate a body with zero torque, and there is a very famous problem with the what is known as Ten's racket theorem. So in Ten's racket theorem, we take zero torque, and so our m with respect to g will be a zero vector, and we take a body whose inertia is so let me first tell you what this tennis racket is. So basically, see, this is not a tennis racket, but it is like a tennis racket. So this is to kill mosquitoes. But okay, so this is a tennis racket. So it has three principal axes. One is this axis, and another is this axis. Okay, that is this axis. And the third one is this axis. So it can rotate about this. If you see this axis, that is, which is longitudinal axis, I can say, the inertia is not that much because the mass is very closer to this axis. Okay, so it is easy to revolve it around this. No much effort is required. I mean, lateral torque is required to rotate it about this axis to accelerate it in this direction. And then we
Moment is,
can see, yeah.
sir, moment will be more in upward direction, I think. Upward
Yeah.
axis.
So this is the axis. If we rotate it in this direction, so we have to apply the maximum torque, okay, to rotate it in this direction. So inertia will be maximum in this direction, and it will be intermediate in this direction. So this axis will be the intermediate axis, okay. So let us suppose we have these three axes. So inertia is maximum in one direction. So let's say it is 15 in this direction, not 15, 5. And let's suppose it is 3 in intermediate, and let's say it is 2 in the minimum direction. And this is 0 and this is 0. This is a 3x3 matrix. Okay, it is a diagonal matrix. And these are the principal inertia, principal axis inertia of this tennis racket. So I was saying that there is a tennis racket theorem or intermediate axis theorem or Janabek effect. It is also known as. So what it says that the intermediate axis. So which axis was the intermediate axis, which is 3. So if we try to rotate it about this axis, so I will throw it. I will not throw it because there is a you can see a length, but you can try at your places. So if I try to rotate it in this direction, I will throw it and flip over it. But when it goes like this and come back in my hand, so it will have completed this rotation about this axis, but it will have also flipped over half revolution about this axis. So this is known as the intermediate axis theorem, and you can also there was a mission going around, I think, in Russia, and they noticed when they were in the space space station, they were unwinding the screw, and the screw, when they unwind, and then it will go into the zero gravity and it will spin. Okay, after few seconds, it will flip over and start rotating in another direction. So it took long time. They kept it hidden and they don't reveal until some paper was there. Then it was revealed. So there was no talk. So why it was flipping? Because if you don't have any torque, the angular momentum vector should not change. This is like how the things were going. So, but it was not like that. You can see, you can simulate these things and you will see that if you have these three axes and you have the inertia maximum in one direction and inertia minimum in another, and there is some intermediate axis, and it was shown that inertia, this body or the rotation about the intermediate axis is unstable. You cannot perfectly align the omega vector with that intermediate axis. If you can, then it is okay. It will just keep on rolling, revolving around there. But if you can't, then it is unstable about that axis and it will flip over. Okay. Similar to this, like if you throw the mobile in this direction, so you see also it also flips because this mobile cell phone, if you see, this has also one axis this, another axis this, and another axis this. So this axis is the intermediate axis. When you try to flip over, you have to perfectly throw it. Only then you can get over it like this. Otherwise, it will make a flip. During this, it will also flip like this. So you can try out these with the tennis racket also. So oh yeah, so one may say, okay, the angular velocity, when it goes like this, the angular velocity vector is in this direction. When it flips, so that angular momentum vector changes. But there is no torque. How can an angular momentum vector change? Okay, so this seems a contradictory, isn't it?
So that was my question.
My question is,
Okay.
this mobile are a nut which is in free space. There are no forces acting on it. There is no torque acting on it. So when it is rotating in some particular direction, so the angular momentum, sorry, the angular angular velocity vector will be pointing in this direction. So when it flips, the flipping means that the angular vector is changing. But since there is no torque, how can the angular momentum vector change? So the thing is that this equation never says. So so let us go back and see like what these equations say. So we have angular momentum about about g, and this is equal to rate of change of. Let me complete. So we have angular momentum rate about g equal to the torque about g, and we have assumed this is 0. So it means the rate of change of the angular momentum is 0, which means that h with respect to g is some constant. Okay, so the angular momentum is constant. This is what our equation says. Okay, so you are asking something. Go ahead.
Yes, sir. I was saying that sir, the addition part of this sir, torque about G is equal to I dot W with respect to fixed plus WB cross I dot omega. I think that the uh, change in the omega when it flips in another direction is due to this additional.
Yeah,
Correct, sir?
yeah, you are also saying correct. That is not different from this. Uh, but see, like, what was the confusion and why was the confusion? It was because of something. Okay, that I want to point out. So till now, the equations are saying this, that if external torque is 0, the angular momentum should be conserved or the angular momentum should be constant. But what angular momentum is equal to? So angular momentum is equal to I dot alpha, I dot omega, and this should be conserved or the constant. Okay, so this should be constant. So it means that I dot some dot product of tensor with a vector should be constant. It is not restricting that omega should be constant. So before this, we usually try to align our omega vector with the angular momentum vector, which is not the case. So this changes, this I changes, this omega changes. During flipping, I am saying omega changes, I changes such that the dot product of tensor with omega is a constant vector in space, and that constant vector is the angular momentum vector. Okay. Did you get it?
Yes, sir.
Yeah, omega vector can change with 0 torque, but angular momentum vector can't change. It can't change its direction. It can't change its magnitude. Both of these are conserved during 0 torque. Okay, so I will show. I will quickly show a simulation where you can see the flipping. I actually few months back I code this and I will show you how flipping happens. So this is a cell phone and I try to flip it. Okay. So but you can see that instead of going around, and there is no torque acting on this cell phone. Okay, there is 0 torque. But even with 0 torque, you can see the angular momentum vector is continuously changing. So it is also flipping. Okay. So see, now it is rotating about this axis, but it has become unstable and it flipped over. Okay, and then going back. Okay, so you can simulate these things using the same equations which I have shown to you. So using all these equations, you can do it. Have you any question or shall we start? Yeah. Hello.
Sir, there's a little bit of confusion in this that uh, change in the angular momentum and change in the angular velocity.
Mhm.
Sir, when there is no torque, when there is no external torque, omega
Yeah.
vector can change, but angular moment can't change.
Yeah.
Sir.
This is not
So,
something we. Yeah. Go ahead.
but uh, how it is possible that omega is changed without external torque?
Yeah, how it is possible? So the possibility comes from this equation. I dot omega
During
equal to constant.
okay, okay. When omega changes, I may be reduce or I may vary.
Yeah. See, I is not something a scalar thing. It is a vector thing. I told you, just it is not a vector, it is a tensor. But I am saying just like vector has its components in different directions, similarly, I has different components in different directions. So when you take the dot product of omega with that tensor, it produces a vector which is in a fixed direction. So omega changes, this I tensor changes such that the dot product of this omega and I remains constant, which is nothing but the angular momentum.
Now I got this.
Got it? Okay.
Till now,
Any other question?
till now, I assumed I was assuming that this I is a fixed quantity. This I is a constant quantity.
No.
But
This I is not a constant guard. I told you this I was a quantity taken as a component in the body frame. Okay. Otherwise, if you see from an inertial frame, this I is continuously changing its moment, changing its component. And let me give an equation to you. So if you want to use it, you can use. So inertia tensor components in fixed frame is equal to inertia tensor in body frame dot inner rotation tensor dot inertia tensor in body frame transpose. So this is the inertia tensor in fixed frame. And since this R is continuously changing, that means this inertia tensor in fixed frame is continuously changing its components. Why this R is changing? From this R dot. Since there is omega, there is R dot and other things going on. And you can calculate this at each instant of time. You have to calculate the components of this I in fixed frame. Given that you have components of I in body frame, which is fixed, I can understand that this thing is constant, this thing is constant, but this is not constant. This is continuously changing. Your body is rotating. And how this body is rotating, that is governed by omega. And how omega is changing, that is governed by this thing. And how this thing is governed, this is governed by this thing. So these all are coupled with each other. If you try to get the analytical solution of this equation, this is not so simple. You can simply, like for zero talk, you can get some equations, but it is not so simple. So it is better to simulate these things and see how the things are going on. Okay, because for simulating things, you just need the derivatives. I hope it answered your question.
yes, sir.
So if you have no question, then we can close it. Yeah.
Yeah.
Okay. So this was the final lecture for this course, that is applied dynamics. It doesn't mean that the applied dynamics has over. I can tell you that it is just the starting for the dynamics, applied dynamics. So you have got a good start if you have understood this course, and now you can explore the big universe of the applied dynamics. Okay, so let's stop the recording.